Hello everyone. Today's lecture. This lecture we're going to focus on the maxima flow problems and solving maxima flow problem with the Python. We're going to introduce the three different tools we can solve maxima flow problem. And the first is using the NetworkX package, library. Second is using the OR2 provided by Google. Finally, is using the SciPy library. Okay, let's start this. In the beginning, we import some libraries in Panda data frame, which is we're using to create our network in Panda data frame. And then we import NetworkX. Of course, we imported matplotlib for plotting visualization purpose, and NumPy as well. So this portion is just give you some parameters using our visualization. All right, this is the description of our maxima flow problem. The maximum flow problem and minimum cuts problem are another simple case or the special case for the general network flow problem. The initial work is provided by Ford and Fulkerson in 1956. Okay, the definition is a graph G with a set of node N, a set of arc E edges E, and each one of the edges has a capacity of Uij. Our goal is trying to find out what is the maxima flow I can send down to this graph from source node to the destination node. Okay. And for this example, the the decision variable is Xij, represent the flows on the network. Okay. Cij is the maximum capacity we can transport on the edge ij. B is the supply node demand and the supply and demand on each one of the node. All right. For the maximum flow problem, the right-hand side BI are very special. For example, for the source node, I equals to 1, as we illustrated here, trying to send down the maximum flow, as is capital F, which we're trying to maximize. Okay. And for the destination node, if the destination node, I have a demand of F. And this F is also a decision variable, which is we're trying to maximize. For the rest of the node on the graph or the network, their node demand and supply equal to 0. Therefore, they are all transshipment node. Okay, so illustrated example looks like this. And Xij belongs to non-negative, actually, and we don't have to have integral constraint because it's the node and arc incident matrix structures is total unimodular. Okay, and so if the right-hand side is the capacity is integer, and the right-hand side will be integer, and all the solution will be integer as well. So here we have an example from Wayne Winston's textbook in 2003, and I give the problem where they come from. And this is an example network we have from the exercise portion of that textbook, trying to send down the maximum flow through the source node to the destination node. So actually we have a total of 6 nodes. All right. I'm going to mark the source node as node 0 and the destination node, the sink node as the node 5. So here we're going to create a Panda data frame. and including the source and the destination. And so you can follow the graph actually going through the source and the target and destination. And the key for each edges is A, B, C, D, E, F, G, H, I. And the capacity on each one of the edges or the arcs. And I specifically colored them into a various different color. Just show you how everything's done. Then I'm saying, okay, I'm going to add the panda from the edge list. Okay, from the edge is a panda data frame. I'm using the edge key, which is A, B, C, D, E, F, G, H, I, J, H, I. And the edge attribute equals to true. So I want to have all the key, all the capacity, and the color imported as well. And created using a digraph, which is a directed graph, which has the arc has a direction, flow direction. The next portion is fairly standard. We did it many times. We give the node position. Okay, we give the edge color, extract from the color portion of our different panda data frame. We'll draw the network. Okay, draw the network. No color equals to kind of brownish yellow. Edge color based on the color we defined here. So we extract those color from the graph directly using the get edge attributes right here. Then also I'm including the edge label using the capacity as is label. So here, very standard, we did many times in our Python tutorial, and then we display the graph. All right, so this part is pretty standard. We've done it many times in our example. So I'm just going to walk you through all these. And also I show you the edges panda data frame. Looks like this: source, target, my edge key, the capacity, and the color. Okay, and I show you some of the components in our graph. We defined it in NetworkX. Solving the maximum flow problem is fairly simple for NetworkX. It's just calling the maximum flow, giving the graph, and the source node is 0, the destination node is 5. That's very simple. It returns two things. One called the flow value, which is the maximum flow value, the objective function, and the flow dictionary. So you can see that the flow value is total is 9, the maximum possible flow on this network. If you notice that what are the the color means, and all the red edges are the cut on the network, which means the saturated arc on my network is 0, 2, 1, 2, 3, 2, total is 7. And then maximum flow from 3, 5 is 2. So over here, total 7 units can be coming into node 2, but no, the arc 2, 4 and arc 4, 5 has a capacity of 8, so they're not going to be saturated to their capacity. So maximum flow is 7 plus 2, totals 9. Particularly choose this particular example is for showing you sometimes the minimum cut and the maximum flow are not so obvious in the sense for the source destination separation. And we'll talk about that in the maximum flow lecture already. So solving that, we fairly easy. We can find out the flow dictionary, which means for node 0, I'm flowing into node 1 with a flow of 6 flowing to node 2 with a flow of 3. For node 1, going to node 2 with a flow of 1, going to node 3 with a flow of 5 in that case. For node 2, I'm flowing to node 4 with the optimal flow of 7. And for node 3, I either go to node 2 or node 5. For node 2, I have a flow of 3. For node 5, I have a flow of 2, so on and so forth. So you can see that, which is the red arc on this illustration. Okay. So we can using the shortest argument path algorithm to solve this as well. Very simple NetworkX algorithm flow using the shortest argument path. We can solve also. And also we can specifically specify using a specific algorithm called Edmond-Karp, which is one of the most popular algorithms we use. We import the Edmond-Karp algorithm directly, and syntax is almost similar to the original. Okay. Finally, we can also using a so-called corresponding minima cut algorithm to solve that, and we just simply call minima cut. And here we have a reachable and non-reachable partition. Okay. Cut value, I'm printing out cut value over here. So maybe you should probably explore here, what is the content of a reachable, what is the content of a non-reachable part of the partition. Here we're trying to, okay, using the cut set and printing out the cut set, which is 0, 2, 1, 2, 3, 2, and 3, 5. And I illustrated it on this network already. Okay, all the red are the cut set. So this part is fairly simple in a sense. Next part is solving the maximum flow problem using OR2 provided by Google. I'm going to import OR2, Python, and a maximum flow. Okay, create a model called maximum flow, simple max flow library model. Import the model, starting node, ending node, and capacity. Very similar to what we have in the beginning. Source, target, and capacity. Here, since we don't do, for OR tools, we don't do any of the visualization here. So I'm just needing the 3 data, which is a source, destination, and capacity. All right. Adding the arc with the capacity using the starting node, ending nodes, and capacity. Very simple. And solve the model. Okay. Between 0 and 5. And print out the result. If the status equals to optimal, then I print out a result. Otherwise, I say, okay, there's a problem with the data. So here is the way OR2 of presenting the solution. Okay. Very similar layout. Finally, is introducing using the SciPy library. SciPy sparse a CS graph library to solve the maximum flow problem. Okay. We trying to import the corresponding library called CSR matrix and import the maximum flow algorithm library. And I create a graph using the CSR matrix. I'm trying to find the maximum flow function for the graph. starting from 0 to 1. This is a very simple example. We only have two nodes. Actually, one is source, one is the destination. I just want you to know the the process. Okay, I can even specify several different method or algorithm to use to solve this maximum flow problem. And the maximum flow on this example is 5, which is easily verified. Then we get another a little bit more complexity is I have 3 nodes, 0, 1, 2, and doing the same. Finally, I'm using an example from the Introduction to Algorithm book, chapter 26.1. I'm using a little bit less trivial example to this. Again, for the SciPy, you're using adjacent matrix. This is the source destination matrix and trying to solve that problem. All right. So here, this notebook, we introduce 3 different Python package. One is the NetworkX. The second is the OR tools. The third is the SciPy library to solve maximum flow problem. At the end of the notebook, I want to mention the maximum flow algorithm can be used to solve a so-called bipartite matching problem, which is an assignment problem in a sense. Our graph is separated into U and V. U is the supply node set, and V is the set of node for demand. So this is an assignment problem. So therefore, we want to assign maxima possible assignment. We call it maxima cardinality matching from U to V, the set of node U to set of node V. And E is the set of the edges on the network. So we call the maxima bipartite matching algorithm. This is how we do construct our CSR matrix. Okay, and using the maxima flow algorithm to solve this problem. And the result will be the maxima cardinality matching, okay, for the bipartite graph. So here we give you a very simple, straightforward summation of a various package can be used to solve maximum flow problem without solving a standard LP or IP integer programming models. So these algorithms can be used many other places for visualization, as a sub-algorithm for solving your actual problem. So here, this is what I'm trying to do is, many times we say, why we don't just using the standard linear programming model or integer programming model to solve the network flow problem or maximum flow problem or the shortest path problem or the transportation problem. And because these algorithms are especially designed for problem structure like this, and they can be handling much bigger problem set, and also they can streamline your solution process in a sense, okay, without going through the standard linear programming or integer programming model. Later part of the semester, we will go through some of the example to see if a network problem with additional, we call it side constraint, which is a standard linear programming or integer programming constraint, how we can interactively using the network algorithm with the standard integer programming or linear program solver. So go back and forth to solve these type of problem. All right, I'm going to finish this set of video. We're going to have a next video talking about various methods to solve shortest path problem as well. See you in the next lecture video. Bye-bye.